Hello students, we're going to talk about a transistor amplifier design example now. This particular transistor amp has the following specifications. We want a gain of 10, we want an input impedance of 20K, an output impedance of about 100 ohms, and we'll assume our transistors have a beta of about 100. The challenge in this particular kind of amplifier is to determine which of these specifications is the most restrictive, and so that's the point at which you need to begin your design. There's a lot of flexibility in many amplifier designs, and one of the most confusing aspects is to figure out where to start. So what we'll do is write down here the theoretical expressions for these specifications. The gain, which is right here, is the ratio of the collector resistor to the emitter resistor in the gain stage, which is this common emitter amplifier centered by Q1. The input impedance involves the bias network coming into Q1, these two resistors in parallel, along with the input to the base of Q1. And so it is equal to R1 in parallel with R2 in parallel with R4, the emitter resistor of Q1, times beta plus 1. The output impedance, on the other hand, involves Q2 and what Q2 sees at its base, which is the output of Q1 on the collector. So the output impedance is R5, this resistor, the emitter resistor of Q2, in parallel with the source resistance seen by the base, which in this case is simply R3, the emitter resistor in the common emitter amplifier. And that's divided by beta. So in many respects, this is the most restrictive one. And the reason is, in general, this term here dominates. And so we'll approximate this by saying, as a first pass, that the output impedance is simply R3 divided by beta plus 1. So with that in mind, we use the fact that beta is 100 and we want our output impedance to be about 100. So we have 100 ohms is equal to R3 divided by 100, which gives R3 equal to 10K. This anchors our first number for the design. That 10K is going to go right there. Then the gain establishes R4. We can see that a gain of 10, which is equal to 10K divided by whatever makes it 10, puts 1K for R4. So that sets the first two values. The next thing that is important to consider is what is the operating point or center voltage at the output of a particular transistor stage. Usually you want to center the output. That is, I want to have, if that's the supply voltage and that's ground, I would want to have this point right there at about halfway between the two. So I would want to make that point there about 7.5 volts. This in turn implies that the base should be 8.1 volts. Along with this voltage here, and this voltage here, and this resistance, that determines the quiescent current, that is the current through the collector, and also the emitter of Q1. It will then determine the voltage at the emitter of Q1, and thereby determine the voltage that we want at the base of Q1. This will in turn determine the ratio of these two resistors to set that voltage. So let's go through that step. I will now take to find the quiescent current of Q1. I have Q1. Quiescent current, is going to be equal to 15 volts minus 8.1 volts divided by 10K. And I've already done that calculation on my calculator. It comes into 0.69 milliamps. 0.69 milliamps into a 1K resistor, of course, makes this point here 0.69 volts above ground. And that means that the base of Q1 is going to be 1.29. That is, I add so V of the base of Q1 is going to be equal to 0.69 volts plus 0.6 volts for a VBE drop, and that gives us 1.29 volts. So with this voltage here, that voltage is going to be dropped across this second resistor R2. I know I'm going to have the difference of voltages between 15 volts and 1.29 dropped across R1. So this implies that the ratio of R1 to R2 should be of the order of 15 minus 1.29 volts divided by 1.29 volts, which is equal to 10.62 as a ratio. Okay, so with that in mind, then we need to determine what values of R1 and R2, along with the known value of R4, gives us the desired input impedance. So if I write out Zn in terms of its actual calculation, I would get that this is equal to 1 over R1 plus 1 over R2 plus 1 over R4 times beta, or beta plus 1, which are about the same. And I want this to be equal to 1 over 20K. So R4 times beta is going to be equal to 1K times 100, or 100K. Now 100K is a not insubstantial portion of the 20K when it's in parallel. So what we can do is we can say that we want 1 over R1 plus 1 over R2 to be equal to 1 over 20K minus 1 over 100K, which, if you work it out, comes to 1 over 25K. That is, the Thevenin equivalent resistance, if you will, of R1 and R2 should be equal to 25K in order to give us an input impedance of 20K. Now I also have this relationship, 10.62 ratio between R1 and R2, so I can then write that 1 over 10.62 times R2 plus 1 over R2 should be equal to 1 over 25K. And if I work through the math, what I get is that R2 should be equal precisely to 27.35K, which I'm going to round up to 27K. So that would be equal to R2. That would put us in the approximate range of our input impedance. And then I would just multiply this by the 10.62 to get that R1 is then going to be equal to 10.62 times 27K, which is equal to 286K, which again, the closest value is 290K. So that is going to give us R1 and R2. So this is going to be 27K, this is going to be 290K. And that sets the resistances for the transistor amp Q1. The last step then is to find a value for R5. R5 can be almost anything you want as long as you don't get the quiescent current too high. So what I'm going to do is I'm going to set R5 to give a quiescent current of 2 milliamps. I really can take almost anything I like, and I'm just going to pick 2 milliamps out of thin air. So I'm assuming a quiescent current of 2 milliamps with 7.5 volts, and that's going to give us a value of say 7.5 volts divided by 2 milliamps gives us something which is on the order of 3.7K, and I'm going to round up to 3.9 because that's the closest standard value. So that would be 3.9K. Okay, so that's our whole design that we need for this little transistor amp. Now once you have completed the design, you really should go and check. So what you want to do now is to go and calculate the values of the various impedances given the known resistances that you have applied, and see if they come close to what you expect them to. So 10K there, 1K there, 3.9K there, 290K there, 27K there.